Hello everyone. So in the first video of RC circuits, today we will see the very fundamental circuit, which is a simple one resistor or one capacitor is there. Okay. So this is the very basic connection of resistor and capacitor that we, I think, always seen this thing whenever we have prepared or the RC circuits. We have seen this is the very fundamental combination of resistor and capacitor. Okay. So the thing is that I want to know here the output voltage and the current across the capacitor, which is also the current across the resistor. Okay. So what are the input excitations possible to our circuit? So we can give two types of the input. One is the input voltage and other is the input current. Okay. So now depends in what kind of input we are giving, whether it is a current or voltage input, we can have many possibilities. Like we can have the different nature of the excitations, like some DC source can be there, some sinusoidal can source can be there, some impulse source can be there, and a step or any pulse input can be there. Okay. So after that the point comes, if there is a possible combinations of different inputs to our circuit, so what will be the circuit's response? So what is the fundamental way of saying directly at the output or directly the response of the circuit? Okay, so we can have the different frequencies input excitation also, which, as we know, the input excitation if sinusoidal has some particular harmonic frequency, let's the sine of the omega m, that is the input frequency of omega m. Okay. So what is the possible? I can have this input excitation of, let I is called V in can be the DC voltage. It can have this frequency component, like if it is a sinusoidal. Okay, if it is a sinusoidal, or if it is a any step, impulse, or whatever possible input. So they all have some frequency. Let sinusoidal has some frequency omega m, that we call, also for the frequency we call f of m. And the sinusoidal and impulse have some infinite sort of frequency, means very high frequency. Okay, very high frequency. Because we know that a signal which is changing the position instantly from 0 to 1 or high to low, whatever we can say, it has the infinite frequency. Infinite frequency simply means we are changing the state of the input in no time, or ideally say means in very less time, ideally no time. Okay. So the possible inputs are DC inputs with a zero frequency, that I call f equal to 0, and frequency sinusoidal or a step or impulse signal, and the pulse also can be there. Okay. Same thing can be applicable for my input current as well. It can also be DC and frequency. It can be a DC current source with the frequency 0, and it can have the some signal which is a frequency not equal to 0. Okay, so the one thing that should come into my mind is that if my signals or if my input can have the nature like a frequency, so directly I would say whatever my input, whether it is my input voltage or my input current, they all are the function of some frequency. Okay, so whatever the nature of the input, you can have, they are the like function of frequency. Simply, if I say my input voltage is suppose 5 volt DC, and what I will say, I'll say there is nothing but a frequency is 0. And if my input is some sort of, like I will say Vm sine omega m t, and what I am seeing here, I am seeing the frequency is omega m, or also I can say frequency in f of m domain, like it is f of m. Okay, so any other signal that I can say v in of, let's say 5 u of t, then what is there, we have the frequency infinite, okay, or can say large, very high frequency, very high frequency, or the signal is changing this position in time 10 to 0. Okay, so what common thing that I'm observing is the frequency. Okay, so if my input is the frequency is input, if my input is the function of frequency, whether it is a current or voltage input, then I would like to see some sort of output is also the function of frequency. My output is also the function of frequency. So it means if my output and input are the function of frequency, then why I'm not analyzing my circuits completely converting into the frequency domain? So what I can see, then my circuit should have some sort of some sort of frequency dependence. Okay, yeah. So circuit should also be have some sort of frequency response, because I am seeing the input is a function of frequency, whatever the type of input is, and also we will see that output will also some sort of frequency. So between the input and output, there is a relation which is nothing but a circuit. So circuit should also be have some frequency dependence, or I will say what is the frequency dependence of these components what we are using here in the RC circuit. So according to that, we'll calculate the output. Okay. So what is the dependency of resistor on the frequency? So we will see resistor is independent of frequency, independent of frequency, and capacitor is the function of frequency. Capacitor's impedance can be the function of, or is the function of frequency. Okay, so what I mean to say, if I write xc, we all know it is nothing but 1 upon sc. So what is this? It is nothing but 1 upon omega c. If I write the magnitude here, because I can write a omega s equal to j omega. Okay, so xc's magnitude is 1 upon omega c. So it is also the function of frequency. Okay, so one thing is very clear. So now if we're doing any intuition, I would like to go at the output by using some frequency relation. Okay, so this is my input, this is my output. And input is also some sort of function of frequency. I will say input I can write as input of s, I can write in this way, and output I can also write output in terms of s. Okay, so what is this? This is nothing but, now I can directly use this simple voltage division. Directly network we can use here. V out of s, V in s. What is the V out of s? V out of s is 1 upon cs r plus 1 upon cs. Simple resistive divider. What do you see? 1 upon 1 plus rcs. Okay. Times V in. Sorry, I would write here V in also. So what is the transfer function? What we are seeing means, what output we are seeing is nothing but dependent on this RC component. Okay, this is the transfer function, or I will say the output is nothing but transfer function times the input. Okay, so this is a very fundamental representation of your any frequency domain representation of the transfer function, which is nothing but some a naught 1 plus s by omega p. This is a very fundamental representation of any first order system. Okay, so basic frequency domain representation of first order system. So I will not discuss about the order. We will discuss this thing some separately. Okay. So what is this A naught? A naught is my DC gain. What is the omega p? It is the pole frequency. Okay, so we will discuss these things later, what is the pole frequency and DC gain. As of now, just understand it what I am writing. Okay, so what I can see, S is my frequency, where S is what? S can be written as j omega. So what I can write, I can write the nature of my h of S, which I will also write h of j omega. I can write it as h of omega, which is called the magnitude, time, or not times, but angle of h of j omega. Okay, so what exactly I can write at the what the magnitude? If I take the magnitude of h of j omega, first I will replace this means s with j omega by omega p. If I take the magnitude, we know what will be this, and the angle means it will be minus tan inverse. What is the coefficient of j, which I will call omega by omega p. Okay, so this is another magnitude and this is the angle. Why negative? Because we are going from down to up, magnitude and angle. From denominator to numerator, when we write the angle, usually whatever in numerator as term, it will contribute to the negative angle, and whatever in denominator, so whatever is in numerator will contribute to the positive angle. Okay, so from here I could see that what is my magnitude. I am interested in my magnitude. Magnitude is my A naught divided by 1 plus omega by omega p whole square. Okay, this is the magnitude. So yes, so what I can see, if I compare these and h of s, what is my omega p? My omega p is 1 upon rc, which I also call 1 upon tau, and tau is the time constant. So why I'm discussing all this, you will understand sooner. Okay, time constant, yes. So now I'm interested in magnitude of h of j omega, which is nothing but a naught divided by 1 plus omega by omega p whole square, and top of that root is there. Okay, yeah, one more thing, from here I will see my a naught is 1. Okay, so in our discussion, what is it? 1 upon 1 plus omega y 1 upon rc whole square, then root on top of that. Okay, so this is the magnitude of what transfer function we got here. It is nothing but a magnitude of our transfer function, which is v out by v in. S I will replace as the omega. So this is the magnitude of our transfer function. Okay, so can you plot this magnitude with respect to the frequency? What I will see, if I make a column like this is the omega and this is h of omega magnitude, I'll see few instants only. Let's say it is 0. Then what is there? It is 1. And if I put the omega as 1 upon RC, what is this? This is 1 upon root 2. Okay. If I put the omega as like infinity or much higher, then what I will see it is as 0. Okay. A simple thing. And now if I want to plot on the curve, then what I will see, so there is some sort of one magnitude for some time, or not for some time, but for some frequencies. And after that, I have seen that this is a f times 2 pi, because I want omega on log axis. So this is my log axis, and I also want this thing to represent in dB. So in dB, it is nothing but 0. But okay, so as of now, I have represented 1, so I will write it as it is. So I am just representing magnitude here, and omega is still on log axis, so not a problem. I want to represent a magnitude here. So 1, and after the 1, we have seen that at a frequency 1 upon RC. After this frequency, you will see at this frequency itself, your magnitude is little down. It is somewhat there. It is practical, but asymptotic plot we see some sort of exact corners, but in actual this is some sort of this. Okay, so there is 1 upon root 2 magnitude at this point. Okay, so this point is 1 upon root 2, what we have seen. So this is called 3 dB frequency. 3 dB frequency. Now my point is here. Okay, this is called where gain is okay. Gain is usually called as 0 dB. So actually this is not a proper representation. This is not a proper representation because of magnitude is 1. The gain is 1. So better the representation will be like in the frequency domain. Our representation will be what? Exactly with this omega on log scale. So 1 magnitude means this is a 0 dB line. And after that it is taking the roll off of some voltage. Sorry, some slope of that we call a minus 20 dB per decade, which I am not talking in detail about it. Okay. So what I mean to say. So here the point here is that okay. Now we'll come to the actual thing. Okay, if the input has the frequency, let omega input has the frequency greater than this omega 3 dB, then what do you see? The output is nothing but less than what we are putting the input, because this is the transfer function. It is nothing but a magnitude of our transfer function. Okay, it is nothing but the magnitude of our transfer function. So output by input magnitude. Okay, so till this frequency, or I will say when omega in is less than omega 3 dB, I will say my output by input, which is called the transfer function's magnitude, is equal to 1, which I will say my output is equal to input in terms of magnitude, means amplitude of output is equal to the amplitude of input. That's it. What will happen at omega equal to omega 3 dB? I will see that the same thing, which is called the transfer function, my output by input's magnitude will be 1 by root 2. So what we can see, my output magnitude is nothing but input's magnitude by root 2. Okay, so slowly what I will see, if I am increasing my omega above the 3 dB, so what I will see, my output magnitude is less than input magnitude. And what to speak of when omega in is much greater than 3 dB frequency, I will say my output is tending to 0. So why I started in this way, the point is here, if I am applying an input and input has some frequency, which you already discussed here, my input is nothing but a function of frequency. Whether it is a DC input means I am applying no frequency input. If it is some AC input, whether it is a sinusoidal input, then it has the frequency, let's say it is a f of m. Okay, so if I can increase this frequency, even the sinusoidal with a higher frequency will not give the output, because we are seeing that with increasing the frequency, our output is attenuated. Output is attenuated. So what the mean? Actually, it is behaving as a low pass filter. So my circuit is behaving as a low pass filter. What to mean by low pass filter? It means it is passing the low frequencies. It is passing the low frequencies and it is blocking the high frequency. Let's say it is some sort of this. So ideally I will say it is passing frequency below this. So this is I call pass band, and it is blocking the frequency after this. This is I call stop band. Okay. So this is not a point to make here about the filters, but yes, you should understand that frequencies less than 3 dB are passed. Passed means I'll get the output exactly as the input is, and frequencies greater than 3 dB frequency, or I will say much greater than 3 dB frequency, will be blocked, or simply I will say your output will be lesser than the input. Okay. Now let's come to the RC circuits and we'll see how it will behave in terms of time. Okay, time and everything matters here. Okay, now this is our RC circuit. I want to see the output and let I am applying some voltage input here. Okay, so if my input voltage is let Am sine of omega mt, and what I will see, I will see my output is nothing but h of means omega times v in, which we already have seen. So what it is nothing but h of omega magnitude, and angle is nothing but h of omega angle times v in. Okay, so what is if the transfer function is 1 upon 1 plus rcs, what is the magnitude? Magnitude is 1 upon root 1 plus omega square r square c square. Okay, so this is the magnitude, and what is the angle? Angle is minus tan inverse 1 upon omega rc. This is the angle. Rest my input is multiplied to this particular transfer function. So what will be the output? Now output is nothing but this signal 1 plus the amplitude is now modified to some value, and phase of the sinusoid is also modified to some value, which is nothing but tan inverse omega, sorry, tan inverse 1 upon omega rc, minus tan inverse 1 upon rc times omega. Okay, so what I mean to say, if I have omega equal to 0, means if I'm applying the dc signal. Okay, if the omega is 0, simply means I'm having the input as 0. Okay, so here the input will itself be 0. So better to say, instead of saying it sinusoidal, I'll say it is some cosine signal. 0 input means no meaning. Okay, I'll say it is cos of omega mt. Just I'm modifying my input so that we can see exactly what we are doing here. Okay, you can change the sine to cosine. Because if the input excitation is 0, then there is a no meaning. Output will also be 0 in that particular case. Okay, yeah. So if okay, so if omega is 0, what it mean to say? Your it means what is there? Your DC gain is what? Your DC gain is nothing but, now it is going to unchanged. It is a AM only. And what to speak of phase? Phase is nothing but phi, which is tan inverse 1 upon 0, which is also infinite. Mean it is pi by 2. Okay. So at 0 frequency, our phase is changed. We can put these values here, and we can see here. Okay. So this is the behavior of the omega equal to 0. Now we can change the omega. We can change the omega equal to omega 3 dB from that response only, which is nothing but 1 upon RC. We will have some different output, and after that, when we put the omega much greater than the omega 3 dB, which is nothing but equal to 1 upon RC, then what we can see, our output, because the numerator is sorry, denominator will dominate as it is infinite or it's very large. So I'll say my output is 0. So what we can conclude from here, our RC circuit, which is particular structure R and C, and we are taking the output across the capacitor, what we are observing that our input frequency is changing and output coming is changing. Okay, so as we are increasing the frequency of input, the output where what we are getting is changing. Okay, so now we can see this thing directly from few instant of the time or frequencies also. Okay, so this is the discussion what we have done in terms of frequency. Now let's see with a few time instants. So if my input is DC, if my input is DC, what I mean to say, my frequency is 0. If my frequency is 0, then what we can see about the capacitor, what we can say about the capacitor reactance, means we want to see the reactive representation of the circuit. means capacitor, what means impedance or what reactance it will offer, and what reactance or resistance, whatever the resistance will offer, you'll see it. So it is what 1 upon sc. This is nothing but in terms of magnitude is 1 upon omega c. So what it is, omega is 0, frequency 0, magnitude is infinite. So infinite means it is open, that you all know. So we can see this thing directly also. If I am applying some DC voltage, then my cap is open, or I would say the cap will not change its state suddenly. Okay, cap has the property, capacitor has the property that is right here. Okay, it has the F equal to 0. My cap is open. Okay, so cap has one property. In general it is not violated, but it is also violated at some places. Capacitor doesn't allow sudden voltage change across it. So what it mean to say, at F very high or infinity, cap will cap will hold its value, what we call VC some zero negative. That is another point we'll discuss somewhere here. Okay, and if frequency is very less, or mean to say DC, cap will not show its presence. It simply means presence. It simply means it will act like the open. Okay, that you can see. So if I am opening this, what mean to say, open network is always like current equal to 0. So now what is the output? Output is nothing but input minus this current times R. So what is the current? Current is 0. So this term is 0. So input is equal to output. That we have seen this thing. If input is equal to output means what is the V in by V? V out by V in is 1. That thing we already have seen from the transfer function itself. From the transfer function's magnitude itself, we have seen this thing 1 upon 1 plus omega square r square c square. And what we have seen at omega equal to 0 or DC signal, my means transfer function is 1, which means V out by V in magnitude is 1, so output is equal to input. That thing we have already seen. So it is happening on some DC voltage. Now, if we are applying some very high frequency, then what will happen? This is happening at DC frequency. If I am applying very high frequency signal, this is my R, this is the C. So if I am applying the signal, F is very high. So what we have seen, that capacitor will not respond. It means if there is a sudden change in the input, high frequency means in time domain, high frequency means in time domain, we can say in time domain, we can say input is changing itself very rapidly. What they mean to say changing itself? Suppose I am on the one state which is called the 1 volt, and from 1 volt my output input is going to 5 volt. And suppose this transition is so fast. Suppose the transition is so fast, I am not taking even a time. When this transition is so fast from 1 volt to 5 volt, this transition time del t is nearly 0, is called very short time, or I will say short time. My input is not taking time to change its states. So in that particular sense, I will say it's a very high frequency. Okay. So in general, if I more elaborate on this concept also, if we have seen the concept of Fourier series, what we do in Fourier series, we actually represent our fast changing signals. It is what we represent means periodic fast changing signals into some sinusoids of particular frequencies. What I mean to say, what you usually do in Fourier series, this is my suppose rectangular pulse. So when it is making itself rectangular, it means there is a sudden transition. Sudden transition itself means very high frequency. Okay, these states in between from this state to this state, I am going very fast in the zero time. So I will say this sudden transition means very high frequency. It means this particular square wave has this square wave has lot of frequency components inside it. Okay, inside it, this thing we can see also. If I'm merging the sinusoids of various frequencies, if I'm merging the sinusoid of very frequency, means this is my one frequency slow sinusoid, and after this one more sinusoid I am having high frequency, after that one more sinusoid of some higher frequency. So now we are combining these all sinusoids, and after that what I'm saying, if I take one instant, that this particular instant, let's say this, as I'm increasing the frequency, let's say it was previously like this, after that it's starting was this. So as I'm increasing the frequency, it is nearly approaching your x-axis. So what mean to say, higher the higher frequency components are making it more like a step changing. Okay, so means higher and higher frequencies component, when the all frequencies components are combined, all frequency components are combined in one square pulse, one square pulse or any step signal. Okay, or in the step signal. So sudden change of the input from one state to another say that it has the infinite frequency component. It has infinite or very large frequency component. Very large frequency components. Okay. So sudden change is saying that we have a lot of in this particular square pulse we have a lot of sinusoids, and sinusoids with very high frequency, nothing but looking at it is changing its state from 1.2 to very high frequency sinusoids, means it is steep very steep means it is suddenly changing its position from here. This is a time domain representation of sinusoidal signal. What we can see, it is changing the states value from very fast from one point to another. We have seen this thing also in the colleges. In the oscilloscope, we can see this thing. Inside the oscilloscope, or any scope that we use in Simulink or in some other tool, we can see in the LT-Spec also, when there is a sinusoid of very high frequency, we are just seeing two states of the output over this one, other, then lower, then higher, then lower, then higher. So we are only observing some sort of this is happening. So this is happening. So sinusoid of very high frequency means only two states are means actually readable or visible. That's lowest state, highest state, lowest state, highest state. What is happening in between we cannot say because the frequency is very high. So this is the only meaning. When frequency is very high, it simply means the input is changing its state in a zero time or in very short time. So what will happen at that particular high frequency? I already told on the previous page, the capacitor will not respond. It will behave like a short, or it will hold its own value. Okay. So if the capacitor will hold its own value, then what will happen? So when my input is the frequency of very high, or I'll say it nearly infinite frequency, then my capacitor is behaving like a short, or it is not changing its state. So it means it is nearly short, because from the impedance of capacitance also we can see This the magnitude is what the magnitude 1 upon omega c, and when omega tend to very high or infinity, it is nearly 0. This is the one way. And other thing is that it will not change its value. So when we are expecting any change, so okay, this is the one way that we can see. This is a one way of showing shorted condition. And other way is that, yeah, other way of saying is that if there is only cap and it is charged to some value, let's say it is having 2 volt previously stored. Okay, now if okay, so this yeah, this is stored here. So what I'll say, this particular plate is on ground, so I'll say this node is on 2 volt. So overall 2 volt is across it. Now suddenly if I'm applying a signal of 5 volt here, suddenly in t equal to 0, if I'm suddenly applying, so what actually is happening to the positive plates of the capacitor? Negative plate is 0. It was previously at 2. Now it is suddenly changing to 5. So I can say it is somehow what is happening at this node, at this particular plate, 2 to 5 volt. So there is sudden change of 2 volt to 5 volt. So what will happen? My capacitor will not respond to this voltage change. I told it holds its value. Okay. So cap will hold its value. Okay. The instant of at the instant of sudden change. So that's why usually we say when we are applying some signal of high frequency or we are suddenly changing the inputs, capacitor is holding its own value, means it is not responding to that particular value which we are applying here. Okay, so it means holding its own value. It means it will just make itself a battery of 2 volt. And what happened here suddenly this point is now 5 volt. This will not care. It will not care. It will show as a 5 volt, sorry, 2 volt battery. If there is some resistive network or something else in the circuit, then we'll say it will charge to 5 volt, but will take some time. But suddenly in that instant it will offer just a 2 volt there. So it means it is not responding to other means changing voltage. So if someone is not responding to change in voltage, some element is not responding to changing quantity, then what you will see? What is the effect of the del quantity there? What is the effect of that del quantity? Its effect is zero. You can see that 2 volt itself 2 volt. It is not getting any del V. So if this 5 volt is 2 to 5 volt is some del V of 3. Some del V of 3 volt is applied, and it has, but the capacitor is having only the 2 volt. It means this capacitor voltage has no effect of del V. I will say the del V across the capacitor is 0. So del V across the capacitor means 0. So how we will represent the 0 voltage? Okay, so how will we represent the 0 voltage? The 0 voltage in general we represent with a short. So with respect to this transition of del V equal to 3 volt, our capacitor is not responding. So it means del Vc is 0, directly means it is short circuited. It is shorted, or it is 0 volt across it. Who is the 0 volt? This del V change. Whatever we applied the changing voltage, that is the amount of 3 volt we applied there on the top plate. So this capacitor is not responding to that particular del value. Rather, it has its own value 2 volt there. But in our analysis, because we are seeing the incremental, okay, this thing I should make clear here, because I am seeing, because we are interested in incremental, because we are interested in incremental voltage only. So our cap has incremental value of 0. It simply means my cap is shorted. Okay, it simply means my cap is shorted. So I think now you got the concept of why we short the capacitor. Just we are expecting any change in the output, so the sudden change or high frequency change. Okay, so we have seen this thing from both the perspective, directly putting omega equal to infinite and making your impedance to zero. That simply means short circuited. Okay, so short circuit has two things. Short circuit has means zero impedance, simply means voltage of 0 volt across it. This is a short circuit. Okay. So now we have seen if this is shorted, what is the output? It is shorted means output is simply ground. So this is my R, this is the cap. Okay. So what we have applied in the second case, the frequency which is very high to large. So it is shorted. Shorted simply means the output is zero. My output is zero. So what we have seen for F equal to zero, my output was equal to input because no current was flowing. When F is very large with an infinite, my output is nearly zero or exactly zero. Okay, so from this perspective, what we can see, you can see two states of output with the frequency. One is here, which is nothing but 1 volt or equal to input, other is zero, somewhere very large frequency, zero. That's it. So my output is somewhere here, something like this. With this thing we already have seen in the transfer function kind of. So what we have seen, when there is a sudden change in the input from particular value of let's say 1 volt to 5 volt, then what I told you, this thing is happening in very small time. Delta t is equal to nearly zero. So when we are seeing any input which is suddenly applied or which is changing its state suddenly, or when we are applying it at particular instant, let this thing is happening at particular instant t equal to zero, then what we can say, because when delta t is nearly zero, so I can say the frequency is nearly infinite. Then only delta t is zero. Delta t simply means time span of changing the states from one to another. Okay, so delta is that span of time. So if delta is nearly zero, means the frequency is nearly infinite. Frequency nearly infinite. That way usually we see when we apply the step signal, when we apply the step signal at t equal to zero, we what we see, t equal to zero means frequency is equal to infinite. So exact this is not a meaning. At t equal to zero it can also be there. At t equal to zero your sinusoid can also be there. Okay, so let's say at t equal to 0 my sinusoid is started applying here, so this has a finite frequency component, let's say fm. So t equal to 0 not always means frequency equal to infinite. This infinite frequency has no relation with this t equal to 0 when we are applying the excitation. Okay, so the infinite frequency component has no relation with this particular time instant when we are applying the excitation. Rather, it has the relation with this particular thing because you are changing the output or the state of inputs in a very small time that called the delta equal to zero. So means the f equal to infinite. For that particular instant, we are saying that because the time is taking very less, at t equal to 0, usually we apply the signal. So we can say t equal to 0 means infinite frequency. Okay, because it is happening because of delta is very small. It is happening because of very small delta. Okay, so I think I could present my viewpoint. Now we'll see in the coming video how better I can analyze this circuit for different inputs, and maybe we'll go through the complete intuition, or then we'll see what is happening on every instant. I'll take few instants and accordingly you'll see the output voltage and current and all other things we'll see there. So as of now, for this video, I think I could represent myself and you people will like it. And if there is anything missing, you can also post a comment or you can ask on a Telegram group or even you can comment in YouTube comment section also. So thank you for this video.